In this part of the operating systems course related to memory management, we are going to cover virtual memory implementation. In paging, every access to memory should go through page table. Therefore, it must be implemented in an efficient way. Page table may be implemented in different ways. For example, it can be implemented using past dedicated registers, or it may be kept in the main memory, or content addressable associative registers may be used. Now we are going to details of each approach. Let us first consider past dedicated registers. Let's assume that there is a single page table consisting of an array of past hardware registers, one entry for each virtual page, and indexed by virtual page number. When a process is started up, operating system loads the registers with the process page table from main memory. Only the operating system is able to modify these registers. The advantages are requires no memory references during mapping. Disadvantages are unbearably expensive if the page table is large, and also loading full page table at every context is needed. Here there's a chart explaining in detail. We have a logical address as a pair of page number and displacement. We have a register which is called page table length register. The page number is compared with the page table length register, and it should be less than that value. Otherwise, it means that it is out of the region of the process itself. If the answer is no, then it means that there is an error. The answer should be yes to continue. In that case, access page table in registers, and this requires register access time to complete this operation. And from the page table in registers, the frame number is received, and it is concatenated with the displacement, and then this frame number and displacement together constitutes the physical address. That address in the main memory is accessed, which is requiring memory access time. So if this is applied, the effective memory access time is, which is EE442, is equal to register access time plus memory access time. Register access time is required to access the page table, and memory access time is required to access the word in the memory. Second approach is keep the page table in main memory. In the second method, the operating system keeps a page table in the memory instead of registers. For every logical memory reference, two memory accesses are required to access the page table in the memory in order to find the corresponding frame number, and also to access the memory word in the frame. This is cheap but a time-consuming method. Here is the flow chart. We have a pair of page number and displacement. Again, we are checking if this is less than the page table length register. If this is not correct, then there is an error. In addition to page table length register, we have another register which is called page table base register. This is showing the beginning of the page table in the memory. If the answer is yes, here page table is accessed in the memory. The entry is at address page table base register plus P, because we are trying to find out what is the frame number for the page. The distance of the page from the beginning of the page table is P. The beginning of the table is written in the page table base register. Because of that, page table base register plus P is accessed to find out the frame number. This is requiring memory access time because page table is in the memory. The frame number from the page table is get and concatenated with the displacement in order to obtain the physical address. And then the physical, the word at the physical address is accessed. This is requiring memory access time. The effective memory access time is calculated as memory access time for the page table plus memory access time for the word itself in the memory. So 2 memory access time is required as the efficient memory access time. For the last approach, we are going to use translation look-aside buffers, or in other words, associative registers or associative memory. These are also called content addressable memory. This is a special hardware that can do search in parallel for a content and provides a result of match or hit or no match, which is called miss. So all this information may be stored in the associative memory. Here there are some information saying that if it is modified or not, if there is a protection, read-write protection, etc. The corresponding frame numbers, and also this is showing if it is valid or not. The content of an example translation look-aside buffer is given here. This is used to speed up paging. This is a mixing of first two methods. Associative registers are small, high-speed registers built in a special way so that they permit an associative search over their contents. That is, all registers may be searched in one machine cycle simultaneously. However, associative registers are quite expensive, so a small number of them should be used. In overall, the method is not expensive and not slow. The flowchart for the use of content addressable associative registers as follows. We have a logical address made of page number and displacement. This page number is used and compared with the page table length register. If the answer is no, that means that there is an error. Otherwise, if the answer is yes, we continue. First, there is a search in the page table in the associative register. This is requiring register access time. If it is found there in the associative registers, in that case, this is called a hit. The frame number is taken from the table in the associative register and concatenated with the displacement in order to find the physical address, and then the physical memory is accessed for the word. This part is requiring register access time, and this comparison and this operation may be negligible, and then there is an access to the memory, which is requiring memory access time for the hit case. However, if it is not found in the associative register, this is corresponding to miss case, and then because it is not in the associative register, the page table entry should be accessed in the memory. So access page table entry in memory at address page table base register plus P. This is required memory access time. At this address, the entry is accessed and frame number is get from there and concatenated with the displacement in order to find the physical address. And then the word at that physical address is accessed, which is requiring memory access time. If you consider the timing for the miss case, this part may be ignored. There is a access to the associative register requiring register access time. And then because it is not in the associative register, there is a miss and memory should be accessed in order to find the frame number in the corresponding entry of the page table. This is required memory access time. And then physical address is obtained and then memory is accessed, requiring memory access time. So if we consider the effective memory access time, if we assume that the ratio of finding a page in the associative register is shown by H, so with that ratio, the corresponding entry of the page table is in the associative register. So effective memory access time for the hit should be used. And 1 minus H times with this ratio, effective memory access time miss should be considered. So effective memory access time is H multiplied by the case effective memory access time hit plus 1 minus H time effective memory access time miss. And this is equal to H times register access time and memory access time, this one, plus 1 minus H time register access time plus memory access time and plus memory access time. Register access time plus memory access time plus memory access time. Then effective memory access time is calculated by applying this formula. Here there's an example for the calculations. Assume we have a paging system that uses associative registers. These are associative registers having an access time of 30 nanoseconds, and the memory access time is 470 nanoseconds. The system has a hit ratio of 90%. So we have register access time as 30 nanoseconds, memory access time 470 nanoseconds, and hit ratio 0.9. The values are written again here. Now, if page number is found in one of the associative registers, then the effective access time, this is the effective access time for the hit case, it is 30 plus 470. This is register access time plus memory access time, which makes 500 nanoseconds. Because one access to associative registers and one access to the main memory is sufficient. On the other hand, if the page number is not found in the associative registers, then the effective access time will be effective access time, effective memory access time miss. This is equal to register access time plus 2 times memory access time. So this is 30 plus 470 2 times. The result is 970 nanoseconds. Since one access to associative registers and 2 access to the main memory are required. So we obtained Effective memory access time hit is 500 nanosecond. Effective memory access time miss is 970 nanosecond. The heat ratio is given as 0.9. Then the effective memory access time is calculated as follows. Effective memory access time, H multiplied by effective memory access time hit plus 1 minus H, effective memory access time miss. So we will have 0.9 times 500 plus 0.1 times 970. And if we do these multiplications, it is 450 plus 97. So the resulting memory access time is 547.